Thank you for coming. This talk is practical mobile application attacks by example. So I am the CEO of 70 Security. If you're interested in this talk, there's a lot of public reports on the website. I was a team lead and a pen tester for Q53 and version 1, so you can click on those if you want to read more about those companies. And I wrote a course for inner security about practical web defense, about hacking and defending web applications. I'm the OWASP OWTF project leader, which is one of the OWASP flagship projects. There's some presentations here, and I also have some certification. So, yeah, if you're interested in this talk, these are some public pentest reports from where you can learn a lot, especially these two here. These were about an application that was mandated in an entire country of South Korea. So pretty much everything you should not do in a mobile app is here. There's like a lot of mistakes. And these are more kind of privacy related. What kind of data is the application collecting and stuff like that. So yeah, and these are other pentest reports on the website. If you are interested about this, you can learn more about those in there. So we're going to go through a lot of practical mobile app attacks. There's a game, what is the vulnerability? So I suggest, if this is recorded, I suggest you pause the video and then try to guess what the vulnerability is and then jump to the solution, right? I will have to skip through that because this is not interactive. So let's start with sexy denial of service attacks. So what does this command do? Now pause and try to guess. So this is basically a denial of service, right? So we have a netcat clone, SVD, and it's listening on port 80. And every time you close it, it's going to spawn again. So this is the delay of 0 seconds to start again. And then whatever connects to this port 80, it's going to reply with the output of the yes command, which as it names implies, it's always saying yes, 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 yes. So it's going to send a lot of data. And then we can crash the application and we will get a nice crash like that, right? So this is what the crash looks like. So basically the application runs out of memory and crashes, right? So yeah, and then I'm also going to skip the fixes. You have them on the, you have some mitigation about fixes on the slides, but because I have so many slides, I will have to skip through this, but it's all written here for you about how to mitigate this. Now, on Android, the SD card is kind of the Wild West, right? Because many applications can read and write data there. It can be extracted without even unlocking the phone. So, for example, a regular thief can like steal your phone, extract the SD card without unlocking the phone first, and there's no encryption typically, right? So this all makes the SD card this perfect location for physical attacks and attacks from other applications on the phone, right? So in this case, this was a vulnerability that could get somebody killed because this was kind of an application meant to help the people in a given country to report human rights violations. So we have an environment where potentially police and law enforcement are against the people, right? So if you say that you reported a human rights violation inside of the SD card, then police can take your phone, can extract the SD card, see that you are reporting these issues, see what you reported, and then get you killed or whatever nasty stuff they do there, right? So this is an example of security vulnerability leading to problems in the physical world, right? So yeah, here we have also like first name, last name, address, so lots of sensitive stuff for this, right? Now, another scenario is in the SD card, right? So take a look at this, pause the video, try to guess what the vulnerability is, right? And now I'm going to move on to the solution. So the problem here is that the application is reading text files from the SD card, and then it's loading this text, saving it into a variable, and then this variable, page data, and then this page data variable is being concatenated into HTML here without any output encoding or whatsoever, right? So this results in XSS, right? So What can we do with that? We can, for example, depending on how the application is built, we can do like just basically set up a request, an XML HTTP request that is going to retrieve files from the private data storage of the application. And for this purpose, the Hack Vector website is really useful because you can have like a script and then you do like eval for char code, and then this will give you like the script without any like quotes and all these symbols that could break, in this case, the concatenation, right? Because you want the script to work. This is the eval string from char code is like a way where you don't have any quotes and things work more smoothly, right? So in practice, when the XSS was being executed, this is what the application showed in a dialog. And then this is how you would fix these kind of things. And now let's look at copy-paste attacks, right? So what attack is this? Now pause the video and try to guess by yourself. So the solution is that using CSS only, we can specify that some text of the web page the user is going to view, but they will not be able to select it, right? So this is what this select none says. So using CSS, we are telling the browser that this text cannot be selected, even though it's being displayed. And then underneath this text, we are showing another text which the user cannot see at all, but they will select unwillingly, right? So, and this is the text that will have the actual payload. So for example, if you have a fake tutorial and the user is copy pasting all the stuff to follow some steps, then they can get this, right? So in this website, this mobile app, the way this looked was like just select all this text and copy paste it, right? So you have like some site, and then when the user copies this, in reality, they are pasting something else here, right? So when you click OK, then you would crash the app because the application was being, we are basically overriding one of the files in the application. So this was a password vault application. So basically we are destroying the vault with the export of the log, right? So the user is trying to export the log of the app, but it's really destroying the vault where all the passwords are. So it's kind of a denial of service, but we're using a file override using a path traversal with a copy paste trickery. So yeah, this is another good example. This is how you would mitigate this stuff. And then for spoofing attack, right? So spoofing attacks, basically similar to the copy pasting that you show one URL, but the click goes to another URL, right? So we have, for example, these special characters, right to left and left to right. So we can use these special characters here and we send a link like this, right? And then the application is going to be helpful and say, oh, this is a domain, so I have to put a link for this. So the victim is going to see this, but when the victim clicks on this, they are really going to go to this URL, right? Because we use these characters, so it's really the reverse of what the user sees. So this is another way for kind of phishing attacks and other stuff like that, that sometimes works, right? So you can use this against email applications or chat applications and see what happens. So let's now take a look at URL schema attacks, right? So custom URL handlers and that kind of stuff. So sometimes applications define a custom URL handler. So in the case of the Onion browser, there was a function to quit, which was exposed using a URL handler, right? So yeah, the vulnerability here was that you could provide like an image, for example, and call this URL handler and tell the application to quit, right? So we can invoke functionality in the application, which is a browser in this case, from a page that the browser is visiting. And we can, for example, just close the browser from the page, right? The entire browser, not just our own page. So this is an interesting attack. Yeah, and the reason is this, right? So this is what the code looks like. Okay, so this is how you fix this kind of stuff. And now let's look at logic bugs, right? So for man in the middle, the context is a secure messenger app. So we have a clear text, how to achieve clear text man in the middle for XMPP, right? So chat applications use this protocol, XMPP. So what you can do is when you try to man in the middle, you can define plain as the only authentication mechanism. And then because there's nothing else to fall back to, sometimes the application will say, okay, if that's the only way I can log in, I will try to log in that way. And then the credentials will be sent base64 encoded, and you can base64 decode them and get the user credentials that way, right? So that's another thing that you can do, and this is how you fix this. So now let's look at update checks, right? So if you have an application and it's doing an update check, what's the problem with this? I'll pause the video and try to guess by yourself. The issue is, of course, the update is being checked over clear text HTTP. So we have here clear text HTTP, and it's retrieving a JSON file. So we can modify the response, and instead of providing the URL from where to download the update, we can provide a URL that is really a phone URL, right? So because we're attacking mobile apps, when the user clicks on the update to get the update, instead of getting the update, they are ringing, for example, a premium number, right? So this is one of the attack vectors useful against mobile apps, right? And this is how you fix this. Now let's look at user dialog for SSL warnings. So we have this scenario, right? The application catches when there's like the certificate is invalid and is going to from the user, and the user is going to get something like this, accept non-certificate, always once aboard. And then this is how the user, the application registers a broadcast receiver, right? So on the fly, and this is something important to know, right? Because if you run browser or stuff like that, this will only look at the manifest, but sometimes the application is going to register attack surface like a receiver in the code itself. So you have to look at the code too, right? So here it is registering the receiver, then it starts the activity and waits for a response. And then at the end of when it gets the response, it will unregister the receiver, right? But there's a moment in time where this receiver is going to be listening for intents, right? And this is what the processing of the intent looks like to answer this question, whether to trust the SSL certificate or reject it, right? So it's getting the intent extra for the decision, the intent extra for the choice, and then if the user decides to say, for example, always, then it will store this certificate to trust it forever, right? So what is the vulnerability in this? I suggest you go back and think about it for a while, pause the video, and now I'm going to jump to the solution. So this was a permanent man in the middle from bypass using this, right? So we can send this broadcast receiver an intent that is sending basically the decision and the choice of trusting these SSL certificates forever. And then if we can do that at the right time when the user is being prompted, we can bypass that and get our certificate accepted forever, right? So this is how they would fix this. And now let's look at another man in the middle of XMPP. So another thing that you can do when you man in the middle XMPP, so this protocol for chat applications like Jabber, Facebook and Gmail also have like some chat stuff. So to man in the middle this protocol, one thing that you can do is to set up prosody, and then by default it will run with a self-signed certificate. So if you can get the application to try to authenticate to your prosody server, that means that the application is trusting self-signed certificates. So this is a good test to do in case you face a situation like that. Now let's look at clear text HTTP communications, right? So what's the vulnerability here? Pause the video and try to guess by yourself. So the application tries to get some XML from the server, right? So we have some site.com, some path file, and then the file is saved like so, right? So we have to download file name, which is retrieved from the XML, and to download contents, right? So, and this is how the file is created. So basically, we can modify this media file, right? Actually, this media file was from a library that the application was using. This was not in the response, but by doing a little bit of research, I found that there was this file name thing that we could do with the media file. So in here, we basically provide the path to the preferences, right? Because this was about reporting human rights violations, some stuff like that as well. And in here, we can specify the preferences XML file. Of course, since we control the file, we can also specify whatever hash we want, and then the download URL for the XML file, right? So in the end, we get the preferences completely overwritten with preferences of our choice as an attacker. And then this resulted in a permanent man in the middle, because in this preferences file, you could specify which server you're going to send the human rights violations to, right? So a government, for example, could exploit this vulnerability and get all the population to report the human rights violations to the government instead of to the NGO, right? So yeah, this is how the attack looked like. So in logcat, the messages you could see here, the file was deleted and then the file was copied over, right? So this is how it was trying to save it on the SD card, but with the path traversal, we can basically override the preferences of the application. This is how you fix that. Now let's look at more clear HTTP for iOS in this case. So this was an application that was retrieving a CSS file, and then this CSS file was being used or concatenated inside of the HTML of the page. Okay, so now pause the video, try to guess by yourself. And this is the problem, right? We can modify the CSS file so that when it is concatenated, it closes the style that it was where it was meant to be inside. So we can close this tag and we can use a script tag, and then we can basically get permanent XSS on the application forever, because the server is always going to reply that the file has not changed. Whereas in here, we are getting every time the user opens an article, or JavaScript is going to execute, right? So this is how it looked like, the exploitation in practice. For XSS, this is always a good approach, that you have your own attacker JavaScript, because then you can just keep modifying this file and try from the mobile phone and see what happens. But it's more comfortable because you don't need to insert a payload each time and stuff, right? So this is basically getting the cookies, the location, document title, the inner HTML, so basically everything. And then we get a report back to the attacker, like this is the IP, the user agent, the cookies, the URL, and all the HTML of whatever the user was reading. So we can spy on user behavior of the app and see what kind of news they like or whatever, right? So this was the issue. And another thing that we could do here is data exfiltration, right? Because when things were being saved as favorite articles, then they would run from file. So this is why we have this check here for the exploitation. And then we could read all the sensitive files in a loop, for example, right? So you define like some sensitive files in an array, and then you look through that, just make XML HTTP request to get them, and then with an alert, we can see if we can read them or not on the app, right? So that is the end of the exploit. And this is how this looked like in practice, just reading the files, right? So they call history. And then, of course, we can also get application files. So as long as the application can read it, we should be able to read, right? So this is how this looks. So we need to get the token on iOS, right? Because on iOS, there's a token that separates the storage of the app and stuff. So in this case, this token was inside of the location. So with JavaScript, we could get the token, and then we could read the file, and that's how you would fix this. Now again, I'm skipping all that because of time constraints. And then another one about data exfiltration. If we have browsing functionality, right? So we have an export activity. There's a browser. There's an intent filter, and here we have this, right? So basically checking what the URL is being passed, right, in this query intent extra. And then you need to figure out what the vulnerability is. So just pause the video here and try to guess by yourself. And the vulnerability is, of course, that the file URL scheme is being accepted, right? So this is a dangerous URL because we can, for example, as a malicious application, we can define this URL on the SD card. So as a malicious application, we can write this file on the SD card, and then we can send an intent to the app so that it navigates to this file URL. And then from the still HTML file on the SD card, we can dump all the databases and sensitive files that the application has and send them to an attacker, right? So this would be how it looked like at the time. Yeah, and this is how you fix this. So now let's look at crypto attacks, right? So this was a crypto messenger. Just pause the video and try to figure out what the vulnerability is here. Now I'm going to jump to the solution, right? So we have an arbitrary file write on decryption. The application receives encrypted files, right? So one user sends an encrypted file to another, and you encrypt both the file itself as well as the file name, right? So the application decrypts this and then gets the original file name and creates a new file with the original file name that the user intended. So with this, we can, again, use a path traversal and provide like another path. So when the user decrypts this, we can overwrite arbitrary files within the storage of the app or of the SD card, right? So this is really bad. And now pause the video again, try to guess what this vulnerability is. And this is the solution, right? So this is the vulnerability. We have a string concatenation, message escape for JavaScript on the message variable. So we can, for example, send an email that is like closing, because this is going to be rendered here, right? So we want to close the single quote, add a semicolon, and then we add our payload here. And then we add something at the end so that JavaScript doesn't break, right? So just an A variable, so then it will close fine. And then with this here, we can get the passphrase which has just been defined on the variable above. We can send the passphrase to an attacker, right? And then you can verify this with some netcat listener, for example. Then you get a request like get my secret passphrase. So we can steal the passphrase of the user that opened your email. That is how you fix this. And now let's look at a mandated application in South Korea. So this is the application I hinted about at the beginning. Everybody in South Korea was forced to use this. Parent, children. It was meant for the parent to control the children. You know, when you say whatever in politics that is about saving the children, it's always the stakes are high. So this is what they were trying, but unfortunately, the application was really broken, as these two reports show. So the first time we tested the application was not using any SSL at all, right? So if, for example, there was a child using public Wi-Fi, some bad guy could like get the URL and all the requests and all the stuff going on, right? So, so yeah, there was no SSL at the beginning. Then on the second round, they switched to SSL. So we have this HTTPS here. So we were like, okay, has this been fixed? But then we found that this is how they validate certificates. So now pause the video and try to see what the problem is with this. So yeah, basically we have SSL man in the middle without warnings, because whenever the application receives an SSL error, it's going to proceed. It doesn't matter what the error is, it's always going to proceed. And if the host name is wrong for the given SSL certificate, it's just going to return true. So whatever happens is going to go, right? It's basically ignoring the warnings. Now, pause the video and try to figure out what this algorithm is and what the problem is here, what is the vulnerability. And I'm going to jump to the solution. So the algorithm, of course, is XOR because we have the input becomes the output, and then the same output, if you use as input, you get the same output as it was the input before. So basically, you use the same key to encrypt and decrypt, and you can see that this key is being hard-coded in the app like this, with the bytes like this, right? So this is what they were using to encrypt the, well, encrypt the phones, right? It's more kind of encoding because the key was on the application itself, but it's really encryption, right? So XOR encryption. And then we can use the same key to encrypt and decrypt, and this was the Python snippet of it. And then basically we have like an obfuscated phone number with the hard-coded key on the phone. Run this through XOR, and this gives you the phone number for the user, right? And it had some null bytes here, maybe to make it harder to find if somebody was running strings on the APK or something. So now let's take a look at this, right? Pause the video and try to see what the vulnerability is. And I'm going to jump to the solution now. So here we have another problem, right? So we have a base64 decode of some fixed parameter that is hard-coded somewhere, saved into a string, and then here we get the bytes of the string. So basically, this is the AES key that is hard-coded somewhere, right? So we have the request, right? So first, there's the phone obfuscation using XOR, and then with the request, we have AES, right, with this second hard-coded key, and then we get this encrypted request, right? So basically a useless AES layer with a static key that can be retrieved from the application. So in summary of the implementation of Star Sheriff, we have this disaster of this is the phone number, you XOR it with a key that is hard-coded in the application and is sent in the request like this, right? So the request is then encrypted using AES with a second hard-coded encryption on the application that anybody can retrieve. So these two steps are useless. Then the request is sent, but the SSL validation is completely ignored, as we saw, because it was like proceed for person stuff. And then we get the response back, right? So in essence, the whole thing was broken, and this slide, we just put it together because it was just so funny. It was so broken. This is how you would go about fix that. So now let's look at code execution, right? So this was a cool scenario. It was a CRM application with Google authentication. So to log in, you get a pop-up, right? If the user is not logged in, the user logs in with Google, and then the pop-up closes and sends the data to the application. So we have a login web view that is browsable, and then we have here how the token is being saved that comes from Google. So pause the video, try to figure out what the vulnerability is, and now I'll jump to the solution. So the solution is that we have SQL injection and code execution. Right? So we have this string concatenation here, and you can see that the value that comes from the token is being concatenated into the SQL query like this. So we have a SQL injection. Right? But is this only SQL injection, or is it more, right? Because in this case, the application had like extensions enabled as well. So it is not just that you can run any SQL that you want, but also that you can load any extension, right? So for example, you have a malicious application on the phone. For this, you can, for example, the Just Trust Me exposed module. It doesn't matter, it's just another application. And you just save like with some A's, the test.so, some mimicking like a binary there. Then you give permissions to all the apps. So any app can read this, even though it's on data. And then the malicious application sends an intent exploiting the SQL injection. And it tells the application to load the extension from this path, right? So this was a code execution with SQL injection in a mobile app, which was pretty cool. Well, yeah, and then on Logcat, right, when you were checking, this is what it would look like, right? So it has about elf magic. So this is telling you that the application was actually trying to run this binary, right? Because it's checking if it has good or bad elf magic. So this means that it's trying to run it. You could also exploit this in phones running Android less than 6, using a malicious application that loads, first saves the file at test.so in the downloads directory of the phone, right? And then makes a second request a little bit later to exploit the SQL injection and get the binary to run, right? So this is how that exploit looked like. And this was pretty cool because you would do it from a browser. Like somebody clicks on that malicious website, and then you get code execution on the phone with the privileges of the application, right? So this is, yeah, we get the same but with magic. So now let's look at API attacks, right? So retrieving files from the server, typical use for the API. So let's take a look at this and try to figure out the vulnerability. So the issue is that we have the string replace of dot slash, right? So this looks okay in practice to many developers, but in reality, it is not, right? And I'll show you why now. And then it's trying to read the file, right? So that is basically how that looked like. So you can provide a sequence like this, and yes, the dot slash is going to be removed, but then you will end up with another dot slash, right? Because this pattern, this second slash is not going to be removed, and when you remove this, you still have these two dots. So basically, you get a path traversal, right? So you can turn dot slash slash into dot slash, right? So with this, we can make the traversal work. That is how you would fix that. Now, API leaks for Smart Sheriff. This is what we call the bully API. So basically, the application would leak information based on the phone number. So let's pretend that there's a bad child on the class that he hates all the other children, and he can, like, for example, knowing the phone number, try to log in as the parent in this application that has been mandated in South Korea to impersonate the parent and, for example, not let the child avoid the child from prevent the child from using the phone and this kind of stuff, right? So the bully, you need the bully API to help you, right? So the bad child knows the phone number of the target child, so it says, hey, I know the phone number of this child I want to mess with, and then the API tells you, okay, this is the parent phone number. So with this alone, you can already do some damage. You can call the parent and tell him stuff. But for a bad guy, this would give you the login, right? And then, of course, you can ask Smart Shade, come on, I need the password to be able to log in as the parent and mess with the child. So yes, Smart Sheriff would give you the password too. You could impersonate the parent, right? So this is how this looked like in practice. Yeah, and the passwords were 4 digits strong as well, so quite weak. You could even like brute force it. And yeah, this was another scenario with Smart Dream. There was a similar leak. This is an IDOR, right? So an insecure direct object reference. It was saved on text-to-speech. So basically, when a message contained harmful words, they will saved on a server, but you could retrieve all the messages from all the children calling this API, right? So this was pretty bad as well. This is how you would fix that. And with this, since we only have 34 minutes, this is finished. Now, if you're interested in these applications, these are part of our mobile course. So anybody that takes our mobile course can take it free. If you have any questions, since this is recorded and we don't have interaction, or if you find some of the attacks interesting or you want to talk about whatever else you want, you can send me an email anytime you want. Thank you for coming.